To continue our French morning and hear about individual-based models and Hamilton-Jacobi equations from Sepideh Mirrahimi.
Thank you, Chris, for this introduction. I would like to thank also the organizers for this nice conference and for this invitation. Big regret for me not to be able to be there in person. So I will talk about filling the gap between individual-based evolutionary models and Hamilton-Jacobi equations. And this is a joint work with Nicolas Champagnat, Méléard and Tran. And indeed, my talk will prepare one of the lectures of Sylvie this week. I think it would be the last lecture on Thursday. And so I will try to provide the motivations and introduce the previous works. And then at the end of my talk, I will announce briefly our result, and then the result will be detailed in the lecture of Sylvie in a few days. So the main problem that we're interested in this project is how to take into account the influence of small subpopulations or local extinction in the dynamics of populations. Long-term ecological or evolutionary dynamics of populations may in general be strongly influenced by small subpopulations and local extinction. Local extinction could be, for instance, in a particular area of physical space or the phenotypical space if we are considering evolutionary dynamics of populations. And local extinctions or small subpopulations could modify the speed of propagation or speed of adaptation of the population. And it may lead to the emergence of new traits that are created from some small subpopulations. And then the question would be, how can we take into account such effects in deterministic models? Usually in deterministic models, we have some diffusion term that makes that the solution, the population density is positive everywhere. We don't take into account the small, we don't take into account a local extinction of the populations. And this could lead, for instance, to the acceleration of the dynamics, or for instance, we can see the emergence of new traits from some subpopulations which were supposed to be extinct. So these are some artifacts that we could observe in deterministic models, and the question is, how can we include such effects in those models? We are interested in this question in the particular context of eco-evolutionary dynamics of populations, which are structured by quantitative traits. And so we will consider some models of adaptation of populations which are structured by phenotypical traits. So phenotypical trait could be, for instance, the size of the individuals at the adult age, or it could be, for instance, the resistance of cells or bacteria to medications, for instance. And so the mechanisms that we will take into account are the following. We will take into account the heredity. That means that the traits of the individuals are transmitted to their offsprings. We also take into account the selection, which means that different traits have different reproduction. So individuals with different traits have different reproduction rates or different survival rates. And this would lead to the selection of the better adapted individuals. We also take into account the mutations, which create some variability in the population, so it creates new phenotypes in the population. And we could consider the competition between the individuals, for instance, for the resources, that usually makes that the population becomes bounded of bounded size. The assumptions that we will make are that we consider populations with asexual reproduction, and we will study only large populations, and we will consider small mutational effects. Okay, so when we consider these mechanisms and under these assumptions, in this framework, what we expect is that the phenotypic density of the population would be concentrated around one or several dominant traits. So here, N is the phenotypic density, X is the phenotype. So this is an example of, I don't precise the model here, but it is in a case where the phenotypic density is a Dirac mass around the point x bar of t, which evolves with time. So here in this figure, horizontally is X, vertically is time, the color is the isolines of the phenotypic density. So we see that the population is concentrated around the dominant trait that evolves gradually to a certain trait that is equal to 0 here. Such type of behaviors can be characterized by an approach that is based on Hamilton-Jacobi equations. And these Hamilton-Jacobi equations are derived in a two-step asymptotic approach. So we have two asymptotic derivations, and the combination of these derivations would lead to the Hamilton-Jacobi equations. The first derivation is starting from stochastic individual-based models, and in the limit of large populations, we will obtain integro-differential models of load-cover type, of non-local parabolic type. Next, from integro-differential models, in the limit of a small mutational variance, which will lead, which means that we will have a small diffusion term in the parabolic equation. In this limit, we will obtain some Hamilton-Jacobi equations. And so we have, and these Hamilton-Jacobi equations then allow us to describe the dynamics of the phenotypic density and, for instance, the dynamics of such dominant trait here. And the thing is that these two limits do not commute. And since the limits do not commute, it is hard to interpret the results of the Hamilton-Jacobi approach with regard to the initial individual-based model. And also it leads to some artifacts. We can have a faster evolutionary dynamics compared to the initial individual-based models. And also, as I said before, no, I didn't say before. So we can also obtain some artificial jumps in the phenotypic distribution. So this is a figure that I have taken from a paper of Pertaman Bar in 2008. So I don't precise the precise model here. We will see the models a little bit later, but we see that, so in this figure, horizontally is time, vertically is the dominant trait. So we have a Dirac mass on this dominant trait that evolves first gradually, but then we have a jump at this point of this dominant trait. And this jump of the dominant trait is usually an artifact of this deterministic model. What happens is that there is some small population here with this trait that normally it shouldn't be there because it has to be extinct. But because we have this deterministic model, there's a small population everywhere. And if it has a good growth rate, then it can win the first population here and lead to the emergence of a new population here that will continue from here, and we'll have this jump from jump of the phenotypic distribution. Okay, but the thing is that such type of jumps of the phenotypic distributions, they could be some artifacts. Sometimes there are some artifacts, but sometimes they also really occur even in the stochastic individual-based model. And this is an example taken from a paper from Billard, Collet, Ferrière, Méléard and Tran, where they considered another model where, in addition to the selection and mutation, they also had a horizontal gene transfer term that takes into account that the individuals can exchange genes between each other. And in this case, so they have ran some individual-based stochastic simulations. And this is what we see in this figure. Here, horizontally is time, vertically is the phenotypic trait, and the color corresponds to the number of individuals. And we see that we have a dominant trait that evolves, and then, we have a jump. We have a cyclic behavior of this dominant trait. And what happens here is that the transfer term pushes the phenotypic, the dominant trait to the right, but the traits which are at the right, they have small growth rates, so they're not well adapted to the population. But for instance, here, the transfer has pushed the phenotypic density to higher, I said to the right, but I have to say to the up because the phenotypical trait is on the vertical axis. So we see that the phenotypic trait has become here, but here it is not very well adapted, but there is a small subpopulation here, which is much better adapted. And this will win to this maladapted trait and will create this new branch that we see here. And so we have this jumps, cyclic jumps of the phenotypic distribution that occurs. And it is actually something that we expect to be biological, and it also occurs in the stochastic simulations. Such type of behaviors can also be recovered by the Hamilton-Jacobi approach. This is something that has been checked in a paper that I have mentioned here numerically, where the solutions of the corresponding Hamilton-Jacobi equation at the limit and the individual-based models are compared with each other. And we see that we can obtain such type of cyclic behavior in the Hamilton-Jacobi approach as well. But now, a question that could naturally arise is that how can we distinguish between the situations where such jumps are for real and with the situations where such jumps are some artifacts? So here is a summary of the motivating questions that we have. So a first question is that, can we derive these Hamilton-Jacobi equations directly from individual-based models? Because previously they were obtained in two limiting procedures. And then how can we take into account the extinction of subpopulations in this Hamilton-Jacobi approach, in deterministic models, and in particular in this Hamilton-Jacobi approach? And then how to distinguish between artifacts and real jumps of the phenotypic distributions. So here, in the project that I present here, we answer positively to the first question here, but our perspective. So in a situation where we avoid the extinction of subpopulations, so it's in the toy model. So we simplify the problem first to just derive the Hamilton-Jacobi equations. But of course, our perspective is to go beyond that and to include situations where we have extinction of subpopulations, and to be able to answer to the second and the third question. Okay, so this is the plan of my talk. I just finished my introduction. Now I will first present to you what I call the Hamilton-Jacobi approach, and then I will present to you a previous work on a deterministic correction of in this approach, and then finally I will present the derivation of the Hamilton-Jacobi approach from an individual-based model directly. Okay, so here I introduce rather classical model in evolutionary biology, a model that is known as the continuum of alleles model, that was introduced by Kimura in 1965, and then it was derived rigorously by Champagnat, and Méléard in 2008. So here, X is the phenotypic density, X is the phenotypic trait, and N is the phenotypic density. So this first term here corresponds to the mutations. So B is the mutation rate, and G of Y minus X gives the distribution of the mutation jumps of size of Y minus X here. So this integral term gives the variations of the phenotypic density due to the mutations. And the next term gives the influence of the selection and competition. Here, R of X and I is the clonal growth rate of individuals with trait X. So it takes into account the best rate without mutations and also the death rate. So the dependence of R with respect to X models the selection. And this parameter I of t is an environmental feedback that is defined to be the integral of psi of y, n of t and y dy. And it can be seen as the consumption of as the total consumption of a resource. Then we will consider that psi of y is the consumption rate of individuals with trait y, and I will be the total consumption rate. And this dependence of R with respect to I models the competition. It means, for this to be a competition term, we assume that R is a decreasing function with respect to I, which means that if the consumption becomes important, then the growth rate will decay. We also assume that there is a positive contribution of all the traits to the competition, so that we assume that psi of x is between two positive constants, bounded by two positive constants. I should mention that Kimura didn't really, so this is not the exact model introduced by Kimura, but he didn't have this competition term, but the type of model is, so the general type of model was introduced by him. Okay, so this is a typical selection mutation model. And in our framework, we will make an assumption that is that we consider a small mutational effects. And we will include this in the model by assuming that the mutation distribution has a small variance. So G of y was the law of the mutation mutations, and so we will rescale it. We will and we'll call it G epsilon of y dy, being defined as G of y over epsilon, D of y over epsilon, and this makes that we are. This means that we are considering a mutation distribution which has a variance of order epsilon squared. And epsilon here is a small parameter. We are assuming that we have a small mutational variance, and this will induce a small genetic variance in the population. And since we need, so the population needs a genetic variance to adapt to its environment, because of this small genetic variance, the adaptation will be small, will be slow, and it will be of order, the time scale of adaptation will be of order epsilon t. And now to be able to capture these evolutionary dynamics, we make a change of variable in time, we replace t by t over epsilon to be able to observe these evolutionary dynamics. And this scalings lead to this model. So which is, okay, so rho here is I, I'm sorry for this. So rho is my I. And so the differences between the model that I showed before is that we have G epsilon instead of G, and we have an epsilon in front of dtn that comes from this change of variable in time. One of the alternatives to model the selection and mutation of quantitative traits. Another alternative that is also widely studied is a model where we replace this integral term for the mutations by a classical diffusion term, or a Laplace term. And this model, so we have this, we have this Laplace term instead of the integral, the convolution term. And this model is valid when we consider that mutations are frequent, but with a small effect. And I have written this model considering constant mutation rates P. Now, once we have these models, the question would be how to characterize the phenotypic density and epsilon. And the Hamilton-Jacobi approach answers to that question. So a first step in this approach is to use the Hofkohl transformation. That is, we write an epsilon to be equal to renormalizing cost constant times an exponential term, exponential of u epsilon over epsilon. And so the idea here is to unfold the singularity of the phenotypic density that we expect to be close to a Dirac mass. And instead of a peak distribution, we will now have u epsilon, which is rather smooth. And we indeed expect u epsilon to have an asymptotic expansion of type u plus epsilon v plus smaller terms. And this u will be the solution of Hamilton-Jacobi equation. Okay. Indeed, if we had a Gaussian distribution, for instance, this u epsilon would be just a quadratic function around the point x star of t. But here, the distribution is not always Gaussian, and the Hamilton-Jacobi approach allows to precise the form of this function. Okay, so we replace this Hofkoff transformation on the equation on an epsilon, and we obtain an equation on u epsilon. So it gives an equation of this form, where we have this Hamiltonian h epsilon of x and u epsilon, which is given in the first model by this integral term. And in the second model, we have this local terms. So it is actually some terms that may recall what Vincent presented in his talk today. So it is putting the Hofkoff transformation and in the equation in epsilon, and we will obtain such equation for u epsilon. And indeed, we can pass to the limit in this equation and show that u epsilon would converge to u, the viscosity solution, to such Hamilton-Jacobi equation. And where in the first model, the Hamiltonian is given by this integral term, and in the second model, it is given by p gradient of u squared. Okay, and so this Hamilton-Jacobi equation is coupled with a constraint max of u is equal to 0, and we have this function I of t here, which is the limit of I epsilon as epsilon goes to 0, and this I of t can be seen as a Lagrange multiplier that is chosen in a way such that the maximum of u remains equal to 0 for all time. Okay, so and this allows us usually to identify, to characterize the function u at the limit. And once we have this function u, we have characterized the function u, then we can obtain some information on the phenotypic density. We can indeed prove that this phenotypic density n epsilon would converge weakly to a measure n of t and x. And the relation between this n and u is that the support of n is included in the set of zeros of u. And in particular, if we can describe the set of zeros of u, we can also describe the set of the support of n. And for instance, if we can show that there's a single point in this set, then we obtain that n is a single Dirac mass. Okay, so I'm not going to the details of the approach and the type of results that we can obtain from this, but I will focus on the artifacts that we have in this approach. So as I said before, we can have artificial jumps of the phenotypic distribution. We can also have fast evolutionary dynamics compared to the stochastic individual-based models. And to understand better these artificial jumps of the phenotypic distribution, it is now interesting to make the connection with this function u and the 0 points of u. So as I said before, the support of n is included in the set of zeros of u. And what happens when we have this jump is that initially, when we are at the left of this figure, the function u has its maximum on this peak, but there's also a small peak at the right that probably for the phenotypic density, it would be too small, probably an extinction of the population. But in the deterministic model, there's still a small population here. And if the growth rate is large here, then this peak will grow up, and at some level, the maximum will stretch to this peak, and at this point, we will have this jump of the phenotypic distribution. there have been some previous attempts to avoid such artifacts. And in these attempts, usually what was done was that some artificial deterministic mortality term were added to the integro-differential model. So a first work on this topic was given by Pertam and Goduchon, where they introduced a model with such mortality term for small subpopulations. And then in a paper with Bar, Pertam, and Souganidis, we studied theoretically that model. And also in a work of Jaban in 2012, he introduced another option for of mortality term, another model. So a question that one could ask is that, does one of these studies provide a good approximation of the phenotypic density, and do they correct the effect of small subpopulations? And how do they compare with stochastic individual-based models? So in the next part of my talk, I will focus on this work with Bar, Pertam, and Souganidis, and I will introduce the model that we studied and the type of result that we had in this work. So what we did is that we added a mortality term to the model of selection and mutation that we had before. So this is the model, the second model that I had introduced before. And we added this square root term with beta epsilon, a constant of type exponential over epsilon, with as negative constant. And the idea was that if an epsilon becomes smaller than beta epsilon, then this term becomes, at the right-hand side, becomes very negative. So we will have dt and epsilon is equal something very negative, and it will go to the phenotypic density will go to 0 at that point. Okay, so we force extinction of the small subpopulations. And so this model was introduced being inspired from a stochastic PDE model that was derived by Champagnat, and Méléard, where they had a term of order square root of an epsilon times a white noise, but we didn't, so we focused, we kept a deterministic model without noise, but we just kept a mortality term of that order. And if we solve numerically this problem and we compare it to the case without the square root term, we see that this threshold can allow to remove the discontinuity of the phenotypic of the dominant trait. Here we have considered this particular form of R. At left, we have the dynamics without the square root term, without the mortality term, and at right, with the mortality term. In both figures, horizontally is the trait, vertically is time, and the colors corresponds to the isolines of the phenotypic density. So we see that we have a jump at the left, but when we add the mortality term, we can the jump is avoided, and we have a continuous dynamics of the phenotypic of the dominant trait.
Sepideh, can I ask a quick question?
Sure.
Can you say something about the motivation for the choice of R?
Oh, okay. So this is just an example where you can find where this type of discontinuity can arise. So it is probably something that okay, I have to remember. So it is probably it has.
You went looking for a nonlinearity, or someone at some point went looking for a nonlinearity where you get this jump on the left, and then you're comparing.
Yes. This is actually very old. I mean, I think that this is an example given in the paper of Bauer and Pertam, and they had some cases where they had obtained this numerically, and some cases where they obtained it theoretically. These jumps of the phenotypic trait. So to be honest, I don't recall exactly the details of how to manage to obtain these, but probably maybe a distribution with two peaks would help. I mean, a function R with 2 peaks would help. But but I have to go to back to this paper to recall what was the more important ingredients to obtain such jumps. But this is something that may happen. I don't think this is an exception. Okay, so it's something that can arise not very rarely. Okay, and there was some numerical analysis given by Pertaman and Goduchon in 2009, where they studied this model with this mortality term, and so they compared numerically this model with individual-based models, and what they showed is that they compared the model without the square root term with the square root term, and they showed that the evolutionary speed is much slower when we have this mortality term, and the branching patterns are reduced. So what I call branching is the fact that the emergence of two or several dominant traits from one trait. So the fact that we could have several Dirac masses from one Dirac mass initially. This is something that couldn't arise in the models that I introduced here because they are too simple. In more complex models, we can have also multiple Dirac masses. And when we have these multiple Dirac masses, so we have these branching patterns that are comparable to those obtained with stochastic simulations when we add this mortality term. A question would be how to characterize the influence of the survival threshold on the solution. And this motivated our theoretical study with Guibal, Bonheur, Pertam, and Takis Yuganidis in 2012. And so I will briefly present the main result is that, so what we did, we studied this model, but in a simplified version. So what we did is that we neglected the dependence of on the competition. So we don't have any non-local term in the model. And we studied the simplified model. And as in the Hamilton-Jacobi approach, we start with a Hopf transformation. That is an epsilon equal to constant times exponential u epsilon over epsilon. And so now we put this in the equation on an epsilon, and we obtain an equation on u epsilon. And we try to understand what we expect to have at the limit. So we see that if u epsilon converges to some function u that takes a value a, such that a has a value that is smaller than our threshold um, then this exponential term will converge to plus infinity and with a minus in front of it. So the term at right will become minus infinity, and this will make that u epsilon will go to minus infinity. Okay, so if u epsilon goes to some value less than um, it will go to minus infinity. And if it goes to some value a with a greater than um, then this exponential term would go to 0. So at the limit, we will obtain the same Hamilton-Jacobi equation that the same as the one that we had before. Okay, and indeed we could prove that we can prove that at the limit u epsilon converges to some function u, which solved a free boundary problem at the limit. Well, we have this Hamilton-Jacobi equation in a certain domain omega, and outside of the domain omega, u takes the value minus infinity, and inside the domain omega bar, u takes the values greater than um. And we have also two boundary conditions. The first boundary condition is the state constraint boundary condition, which means that u is a viscosity supersolution in the set omega and a viscosity subsolution in omega bar. And we also have directly boundary condition, which is that u is equal to um on the boundary of omega. And these two boundary conditions make that we have a well-posed problem at the limit, at least in some situations. Okay, but the problem here is that this threshold that we put and the mortality term that we put was completely artificial. So we didn't have a biological explanation, and we didn't have a stochastic derivation of that. And in particular, it is not clear how to choose this threshold okay, and it is not clear. I mean, a question that we could ask is that could we justify such a model with from stochastic individual-based models? Okay, so this is the main motivation of what we did our current project with on the derivation of the Hamilton-Jacobi equation from an individual-based model. So, so I present very briefly this model, but then it will be presented in more detail by Sylvie in her lecture. So what we do is that we consider stochastic supercritical birth, death, and mutation model. In this model, model, first of all, we consider a framework of large populations. So the model is parameterized by a carrying capacity parameter K that we will let to go to infinity. And individuals would be characterized by a quantitative trait X, which belongs to a torus. And we will consider a discrete space for the traits. So the traits belong to the set I delta K, where delta K is the discretization step of the torus, and the torus is the set between 0 and 1, considering a periodic boundary condition. And delta K is chosen as such that 1 over delta K is an integer, such that considering these sets, we really have a periodic set of points. Okay, and we consider a stochastic process, a Poisson process, which takes the values Nik T, where Nik corresponds to the number of individuals with trait I delta K. And so we have transitions between different states of the population that occur because of some events of birth, death, and mutations. Okay, again, I don't go to the details of the model. It will be detailed by Sylvie. But some assumptions, important assumptions that we make is that we have a supercritical process. So we consider that for all traits, the birth rate is greater than the death rate. And we also assume that initially we have a minimal subpopulation size, that is Nik of 0 is greater than K to the power some positive constant A1. And these two assumptions make that we will avoid the extinction of subpopulations. Okay, so we remain in a simple case where we don't have extinction of subpopulations for the moment. And here are the scalings that we consider. We consider that we have a large population, so the parameter K goes to infinity. We consider that the individual mutation rates are of order 1 and given by a function P of X. We consider small mutation steps of order 1 over log K and a long time scale of log K. We also assume that the discretization step is less than the scale of mutation steps, so 1 over log K, and it is greater than K to the power minus A2, where this first inequality is somehow technical. So once we make these assumptions, we expect that these subpopulation sizes in Ik would be of order K to the power some function beta, and we will define a function beta Ik of t to be log of Nik of t over log K. And this is indeed the same graphical transformation that we had before here. So beta Ik would play the role of U, and Ik will play the role of little n, and 1 over log of K will play the role of epsilon. So it is really closely related to the deterministic derivation. And the idea is that this beta Ik will converge to the solution of a Hamilton-Jacobi equation. Okay, and this is what we prove. So to do that, so at the limit, we want to have something, a function of a variable, a continuous variable. So to do that, we first introduce a function beta tilde tk, which is obtained from an interpolation of beta ik. And then we prove that this beta tilde k converges in probability to the unique viscosity solution of this Hamilton-Jacobi equation. So this is deterministic, the limit is deterministic, and then it is also given by the viscosity solution of this Hamilton-Jacobi equation. Okay, so as you see here, we don't have any constraint in the limit problem. And this is because we neglected the competition. We didn't take into account the competition term. The constraint came from the competition. And also here we have a similar type of Hamilton-Jacobi equation that we had as in the deterministic case. There is no modification. And this is because we have chosen a framework where such subpopulation extinctions do not occur. So the difference would come from the extinction of subpopulation. Of course, this is the main, this would be our objective to go further to be able to include such situations. So there are several perspectives to this work. First of all, we would like to relax these periodic boundary conditions and consider changing growth rate and to include a competition term. This will allow us to consider situations where we have extinction of subpopulations. Because of this extinction of subpopulation, the Hamilton-Jacobi equation at the limit would be modified, and then the ultimate objective would be to study such an equation to understand the dynamics of the population. Okay, so I will stop here and I will be happy to answer to your questions. And if you want to have more details on this model and the result and how we obtain them, then you can follow the lecture of Sylvie, I think, on Thursday. Thank you very much for your attention.
Okay, any questions? Pascal, go for it.
Yeah, thanks, Sepideh. So I don't want to wait 3 days. So, but it was a bit fast in the end. So can you go back to the precise theorem statement? So can you help me parse the first line? So the beta. The definition of beta. So
the definition of beta is just, and I mean, we had beta ik, which was the size of the population taking the trait I delta k. Beta ik, it corresponds to the size of the population taking the trait I delta k, and we wanted to have a continuous function, so we make a simple interpolation of
okay.
So to define beta tk, beta tilde tk of x, we interpolate between the values of the trace at I delta k and I plus 1 delta k.
All right. So beta ik was the size of the population. Okay, and then.
So it's just an affine.
What was the rescaling then again? So.
So the rescalings were given here.
Oh, okay, I see.
I know that I was extremely fast, but don't worry, Sylvie will explain these much better.
Right, but
it's just publicity for.
All right, okay. And this converges, and then, okay. So then, can you then just advance one more slide? So.
Yeah.
Right. So where do you get the cutoff? I mean the cutoff here. How do you see it here in this equation?
So the cutoff, you don't see it because I mean the cutoff comes from the extinction of subpopulations. But so this is really the motivation, the cutoff. But here we just first concentrated on the derivation of the Hamilton-Jacobi equation and not the cutoff. So we chose a framework where we didn't have extinction of subpopulations because we have a supercritical process and initial large population size for all the traits. So it makes that we will never be close to the threshold. So we will never be close to zero. We will not have extinction of subpopulations. But here we will not introduce any threshold. The idea is that we just want to distribution. So if the population becomes extinct for some trait, then we have to take into account. So the threshold will be when we go further and consider situations where we have extinction of subpopulations, a threshold would appear naturally, and it would be, I mean, here it would be like beta will be between 0 and 1. So the threshold will be 0, and the maximum of beta will be equal to 1.
So I have a quick question. So here you're starting with a random object and you're converging to a deterministic one, right?
Sorry, could you repeat your question?
You're starting with a random object and you're converging to a deterministic one, correct?
Yes, yes.
Do you have any hope to get like some understanding of the fluctuations, or is that too hard, or is that a future project?
Well, the fluctuate, I mean, what we do here is that we use the fact that the fluctuations are small. So we show that because we are in a large population limit, the fluctuations are small. And this is what we show. So we use the fact that the fluctuations are small, and then we focus on the deterministic part to describe the dynamics. But I mean, the interesting point of it is that even if the fluctuations are small, with doing this, we will still capture this phenomenon of local extinction that we couldn't capture if we had a deterministic model in the beginning.
Okay, so let's thank Sepideh one more time.